So today, today I wanted to speak about a topic that has been quite prominent in deep learning research in the last couple of years. So I wanted to give a kind of a very brief introduction and overview to mean field theory, which is an asymptotic dynamics result for neural networks that is somewhat parallel to the neural tangent kernel approach. And also wanted to link this to a kind of standard piece of dynamical systems theory, and help provide a bit of background to how results in this area are proved. Furthermore, I wanted to split this topic into a couple of parts. So today, just to give a very brief overview and intuition of what mean field theory is, and its connection to optimal transport. In the second part, I wanted to talk in more detail about the original application, which is that for two-layer neural networks, and see some of the available global convergence results in that case. In part three, I'll give a talk about how the framework extends to deep neural networks, and throw some light on the dynamical systems phenomena there. And part four is potentially left open. I'm not entirely sure about the schedule of the seminar at the moment. Initially, I was planning to stretch the first three parts over four individual seminars. But maybe in part four, it's good to keep it flexible and talk about a kind of a recent new perspective on mean field theory that is coming from a different approach completely, which is that of neuronal embeddings. And this is also kind of to force myself to go through the background for this piece of theory. So basically what we'll try to do is we'll see how we progress through the first three sections, and then in part four, we'll try to keep it flexible. Okay, so to begin, the picture for mean field theory starts with two-layer neural networks. Again, I hope that you'll be familiar with the representation here. The neural network is set up to look like a sum of activation functions, which take in some trainable weights and the data, obviously, in the sort of standard in the standard kind of description of neural networks. The sigma star activation functions, they're what you might expect. So they're linear sums of data and weights activated with something like ReLU or sigmoid or so on and so forth. Obviously, you take in data from a particular distribution, and your objective is to try to minimize some sort of risk over the weights, either taken in expectation or over the empirical distribution. Okay. So now the underlying insight in the previous formulation is that the risk itself only depends on the empirical distribution of the weights, because the individual weights themselves, the sigma 1 up to sigma n, are kind of permutation invariant, right? So you can swap these things around, and effectively the only thing that should matter is the distribution of the weights, right? Either the empirical distribution if you have some sort of finite sum, or as we'll see, when you pass to a sort of infinite limit, what will matter is the distribution of the weights alone. So this kind of perspective is similar to what you get in classical statistical mechanics, which is that the only thing that that governs the dynamics of the system is obviously the position of each particle at a particular point and its interaction with the distribution of surrounding particles, not its individual interaction with surrounding particles, right? And also notice that basically everything is set up to look like, everything is set up to look like a law of large numbers quotient, right? So in that sort of sense, mean field theory is considered to be a type of law of large numbers approximations to the asymptotic behavior of neural networks as the width of the layers tends to infinity. Okay, so the first observation is that for the risk, you can immediately define the risk over arbitrary distributions of weights by first splitting the empirical risk according to its as a quadratic, basically in the weights. If you look at the form of the neural network, in terms of a potential V and a positive semi-definite kernel U, with the appropriate coefficients given here. And then you can replace the sums by integrals to recover the risk in terms of arbitrary distributions of weights. And notice that also F has a similar asymptotic description as you replace empirical by let's say fully supported distributions as an integral over the individual activation functions, or of the activation functions over the individual distributions. Okay, so why is this interesting, and why does this have any connection to the let's say finite time dynamics of the system? Is you can give fairly trivial bounds on the risk, which say that the infima of the finite sum risks and the infima of the distributional risks, these are closely related as n goes to infinity. So in particular, you have this kind of equivalence in the risks of the distributional weights and the empirical weights. So it's actually sensible to have a look at the weights and figure out whether these realizations of the risk actually happen under some sort of convergence phenomena of the distributional weights. So the idea being that under an appropriate discretization scheme, you can show that the empirical distributions of the weights tend to a sort of continuous distribution of the weights, where a particular step size has to be chosen for SGD, and the continuous distribution follows these distributional dynamics equations. If you look at this, it's very similar to an equation that I hope we'll recognize shortly. However, it's important to look at noisy SGD actually before this connection becomes elucidated. So the noisy SGD gradient step, the noisy SGD update step, is given by equation 11, which is your typical, let's say, gradient update step on the weights of the neural network, with added noise coming from, let's say, some independent Gaussian. And now, if you look at the corresponding distributional dynamics equation with a particular chosen step size, this dynamical equation resembles something that is actually fairly well known and extremely well studied, which is a type of Fokker-Plank equation where the coefficients themselves they also have this extra dependence on the row distribution of the weights. So in analyzing this this particular phenomenon, people have looked at, first of all, showing the approximation, showing that the approximation of this equation with the finite with the finite time empirical distribution of the weights is possible. And secondly, studying the dynamics of this equation and looking, for example, for stationary points in the dynamics to understand what the behavior of weights during the evolution of SGD looks like. Okay, so fundamentally, as I said, these equations are very well understood, but the problem that differentiates this from the typical Fokker-Plank equation is the presence of the rho distribution in the coefficients, and this is kind of the object of a different branch of dynamical systems, which is called McKean-Vlasov processes. Again, the solutions here are typically well understood, but for the purposes of this initial part, it's actually quite educational to look at the Fokker-Plank equation in its original form and study its dynamics separately. Okay, so actually, it's a little bit easier to conceptualize if you look at the heat equation. This is the standard heat equation which is known to be an L2 flow on the Dirichlet functional. There is a typo here. This should be a square. And it is the Fokker-Plank equation associated to Brownian motion. The standard Fokker-Plank equation associated to an Ito diffusion SDE is given by equation 16, and you can see that it's exactly the same as the distributional dynamics proposed for noisy SGD, with the exception that the coefficients themselves can I figure out how to close these?
We can just turn off things.
I think they should do it. This is very slow, and I don't know what.
Why you have to look at that?
Okay. All right. So the idea being that in order to understand the flow of weights across stochastic gradient descent updates, this distributional dynamics of the weights equation closely approximates what happens when the number of neurons goes to infinity. And this approximation property is not going to be part of what we talk about today. I'm actually going to spend some more time on in the second part discussing this. The approximation of the distributional dynamics with finite time weights is going to be a separate problem that we're going to look at today. We're going to look at the Fokker-Plank equation itself, and we're going to look at a particular property that was, I would say, only fairly recently well understood, which is its interpretation as a gradient flow in a particular metric of interest, which makes the equation tractable, and also provides global convergence solutions for the mean field theory perspective. So this particular interpretation will pretty much show up in all kind of in all standard papers on mean field theory, and will provide so will provide an interpretation of the stationary dynamics of the equation. Okay. So again, the stationary points for the Fokker-Plank equation, they're fairly well known. It's the Gibbs-Boltzmann distribution. And these distributions are minimizers of the free energy, where E is the integral of the potential psi over rho, and S is minus the Gibbs-Boltzmann entropy. So it actually makes sense to think about this functional even when the stationary states don't exist, and regardless of the existence of stationary states, F is itself a Lyapunov function for the dynamics, which means that it decreases as E tends to infinity. So during the dynamics of the system, this function tends to be decreased, and the question is, do you ever find stationary states? This suggests that rho t may be interpreted as a particular flow of the functional f when regarded suitably, and that there might be some sort of variational principle that would help minimize it. So again, this is somewhat of a standard perspective in machine learning at the moment, but we'll spend a little bit of time looking at this. So for gradient descent in Euclidean space, or gradient descent in Euclidean space is given by the following Cauchy problem, right? The speed of the particle is given by the gradient flow of f at a particular time t with some initial condition, right? The implicit Euler approximation scheme, which looks like what we typically use in machine learning for gradient descent, is given by equation 20. Notice that it's not exactly gradient descent, as that is basically the explicit Euler approximation scheme. Okay, why is this important? Is because in order to view the dynamics of this equation as a correct minimization scheme of the functional f, it's important to be able to move from spaces where you have well-defined gradients to arbitrary metric spaces. And again, this is hinting at something that we already know, which is the Wasserstein space dynamics of the functional. So the idea being that for all types of gradient flow in Euclidean space, you can define a variational principle called the minimizing movement scheme, which is given by equation 21, basically saying that the n+1 iterate is a member of the minimizers of f of x plus x minus xn squared over some particular step size. So notice that if you differentiate the right-hand side here, this actually gives you immediately the implicit Euler scheme. So this is why this particular scheme itself is, for at least for Euclidean gradients, going to give you the same approximation. But of course, it doesn't tell you actually how you extend it to arbitrary metric spaces. Obviously, the numerator in the right-hand side of 21 can be replaced by a distance function, but there's no guarantee that you get a scheme that converges to stationary points, and that's actually a significantly more difficult piece of theory. So in general, for metric spaces, you'll need various things to be well defined, such as the notions of lengths. So you'll need to be able to talk about length minimizing curves in geodesics. You'll need to be able to talk about the speed of a curve, the slope of a function, or the subdifferential of a function, geodesic convexity, plus you need a bunch of assumptions on f, like lower semi-continuity, and you need a certain compactness assumptions related to the distance function. So without getting into details on all of these things, they can be found in the reference section. But the idea being that for the most well-known example of this this problem, which is the Wasserstein metric for probability distributions. A large class of functionals, which is given by 24, 25, 26. So integrals over scalar functions, integrals over potentials, integrals over symmetric kernels. These will all admit well-defined first variations, where the Wasserstein gradient flow under rho is well-defined and is given by this equation. I mean, there are certain technicalities that are involved in showing this, but nevertheless, this is true under mild assumptions for the functionals themselves, so for the integrands. And also importantly, if f, v, and w are convex, f is also displacement convex, so it's geodesically convex under the Wasserstein distance. Okay, so this is kind of a fairly general piece of tech that would immediately resolve the long-term behavior of this equation, because of course it is given in terms of these functionals, but nevertheless, the arguments for showing why the Wasserstein gradient flow and the dynamics of the Fokker-Plank equation are actually much more intuitive and much more geometric in nature. So the idea being that without having to use such a complicated piece of kit, we should be able to see how these things relate and provide a fairly uniform explanation for the dynamics in Wasserstein space. Okay, so yeah, go ahead.
I didn't understand if there is a relationship between the Fokker-Plank equation and this last one that you show. I mean, they seem different, or maybe they are equivalent in some circumstances. I mean, you said that with the Fokker-Plank, it may be that you are minimizing some functional. And are we supposed to see this?
This is the Fokker-Plank equation for f given by this.
Oh, it is.
Yes.
Okay.
Yeah.
But I mean, it's not super clear. Probably just by just looking at that.
This is the Fokker-Plank, right?
Yeah. I mean, if you compare equation 16 and the last equation you showed, the SDE for the geodesic Wasserstein, I mean, I cannot tell they are the same thing under 70. I mean, it's not so obvious, right?
If you write down the first variations of these two things, yes, I think it's so. Okay, so there's some calculation in between, but you need to know what the first variations of these functions look like. So okay, this depends on the first variation of f, right? The first variation of curly f is f prime. The first variation of curly v is just capital V. The first variation of curly w is capital W convolved with rho. So these will give you.
Yeah, let's not get into this. I just want to understand the high-level picture. So the high-level picture here, what you're showing is that a Fokker-Plank equation, which is derived from some dynamics of, for example, of the weights, like gradient descent on the weights, is the same as minimizing this functional using a gradient flow in this space of distribution.
Yes,
that's what you say.
Pretty much, yes.
Okay. That's the summary of this part.
That's the summary of this part. And what I want is to kind of give this idea that there is a more general phenomenon happening for a large class of functionals, including all of the ones that suffice to express the Fokker-Plank equation. But in particular, the Fokker-Plank equation and its connection to the Wasserstein gradient flow is actually much more intuitive. We're going to spend a little bit of time looking at the particular discretization for this functional and show how it relates to the Wasserstein distance, and furthermore show how the iterates of this particular minimizing movement scheme approximate the solution to the Fokker-Plank equation. So this is kind of a particular argument that is extremely standard in all texts surrounding mean field theory, where you aim to analyze the, let's say, the stationary dynamics of the weight distribution after passing to infinity. So the mean field theory has kind of two major types of arguments. One of them is kind of showing this convergence. So this is this type of convergence argument, and then the second one is finding.
Sorry, Alex, we can clearly see your content on the whiteboard.
Yeah, just a sec.
It's a little bit opaque. Yes.
Yeah, you can. Maybe can I try and add different marker?
Yeah, I'll try a different marker. So this is for n tends to infinity, and for epsilon tends to 0, and there is a particular relationship between n and epsilon. So these are not independent. And the second one says finding rho star, which is the limiting behavior of rho t. So this is kind of
I mean, but this second thing, besides some famous cases like the Boltzmann-Gibbs distribution, that's very hard to do, I guess.
So I mean, you don't need an analytic formulation. What you really would like to show for this is to see that the population risk evaluated at rho star is 0, right? This is kind of the holy grail.
Okay, you want to show global convergence.
Exactly. Yeah. So this is kind of the holy grail, right? So you want to see that as the number of weights goes to infinity, and then as you let SGD run as much as possible, you have this global minimizer for the risk. So yes, I agree. You don't really necessarily need to grab an analytic formulation for this thing. Okay. So for the remaining slides, we're going to look at this connection, and the idea being that okay, this minimizing movement scheme is not generally guaranteed to produce, to consistently produce solvable minimization problems. But for the Wasserstein distance in particular, it is under kind of mild assumptions on the potential, and we're going to use this fact to show that when you iterate through this scheme, you get something very closely resembling gradient descent on the Wasserstein distance, and furthermore, its solutions will recover the Fokker-Plank equation. Okay, so this is kind of the main result. It's written in this way, coming from the original paper where it was approved. This is the 1996 paper written by Jordan, Kinderlehrer, and Otto, which is a fairly kind of seminal paper in dynamical systems, something that I also was interested in for a while back. And namely, this is the first paper that makes the connection between gradient descent in Wasserstein space and the Fokker-Plank equation. It's actually quite interesting to remark that this kind of perspective wasn't available until fairly recently, though the theory for this PDE and dynamical systems analysis is actually fairly old, much older than this. So the idea being that the sequence of solutions to 22, when appropriately interpolated, through equation 30. I'm going to actually produce a little picture for this. They tend weakly to a solution of the Fokker-Plank equation, and the initial condition tends strongly, which is a little bit less interesting, but also a fact itself. So let me just clarify theory a little bit. I don't really know if this is from where we stand, but it's something like this. So the idea being that you start from a particular, so H is the step size, right, for this minimizing movements procedure, and you iterate through it and gain new solutions at each step.
What is the x-axis here?
It's abstract. It's not a graph.
So y-axis is the iterations, and
y-axis is iterations. X-axis you can think about it as time. So this is t. Yeah.
What time?
Time t for equation 30, right? So these are all distributions that evolve in time.
Yeah, but they evolve in iterations. So what's the difference between iterations and time?
So, well, both. So the idea is that at each iteration, this is a distribution. It's not really. This is a distribution on R to the n, let's say. Okay, but individually, you can also think of them as evolving in time, right? So this interpolation between discretizations in time is exactly what was happening previously in the weight approximation of the distributional dynamics equation. And it starts off like this, right? So for the initial interval, for t is from 0 to h, this is h, right? The interpolated solution is equal to this. From h to 2h, it's equal to this. From h to 3h, it's equal to this. And so on, right? Like this. Okay, so this is how you construct a time-dependent solution from individual time steps. And the idea is, so obviously this this statement about convergence is taken as h tends to 0. So what happens as h tends to 0 is these intervals contract, right? But also the individual distance between these levels contract. And this is something that you should see from the right, from the minimizing movement scheme, where h is basically a type of step size. You're expecting that rho hk plus 1 and rho hk, they start differing by something that is bounded by some function of h, right? And this will be effectively what brings this thing together to converge to a solution, to a uniform solution of the Fokker-Plank equation, right? Okay, so the proof itself takes a lot of inspiration from the kind of standard techniques in PD analysis. We're not going to go through all of the statements that say how things converge, how you show that various convergence behaviors exist, how you move from like weaker convergence behaviors to stronger convergence behaviors. But we're just going to go through the equations and basically recover the Fokker-Plank equation from the minimizing movement scheme. So we're just going to start with the minimizing movement scheme and recover the Fokker-Plank equation at the end. This is going to be for the next couple of slides. So the idea is that you only have the variational principle given by the minimizing movement scheme to rely on. So all you know is that for arbitrary distributions, these are worse than the minimizer of the minimizing movement scheme for each individual k. So in particular, this holds for anything that is a variation of rho k or a push forward of rho k along some sort of vector field. So what is a push forward? We'll talk about it immediately. The idea being that if you have, I wish I had better markers. So if you have at every point in time, if you have a particular, let's say, influence acting on the plane, there is a time t. There's a time t kind of displacement. So each of these segments gets slightly displaced. Okay. And what the minimizing movement scheme tells you is that all of these are worse solutions than their individual starting points for the minimization problem that's given by the by equation 16. Right. So what this implies is that this differential quotient here is positive for gamma given by effectively the solution for the minimizing movement scheme, for the right hand side of the minimizing movement scheme. Okay, so the push forward, which is the thing that I'm depicting in red on the blackboard, this is the distribution that integrates along test functions as if the test functions were composed with the vector field phi, right? So all of this is arbitrary at the moment. We haven't made a choice of phi and we haven't made a choice of test function. But this allows us to study the limit as tau goes to 0 and recover the differentials of the components of f, so E and S. So in particular, by choosing the test function to be the potential that was driving the diffusion equation, we can recover the differential quotient for E. We can let tau tend to 0 under the right-hand side, and this will give you the derivative with respect to tau because these quotients converge uniformly. These integrands converge uniformly, and you can recover the first variation, the derivative of E composed with rho tau at tau equals 0, which is obviously still related to the first variation of E. Now, similarly, the differential for the entropy, by making an appropriate substitution there, is also easy to express in terms of the vector field that you're pushing off against. Right. So this helps you compute the value of d of d tau of f of rho tau along this vector field psi. So the only thing that you need to do at this point is to evaluate the differential quotient for the Wasserstein distances themselves, right? So the difference in the Wasserstein distance between rho t and rho k minus 1. So it's effectively this minus this. right? So the idea being that as t goes to 0, this this should also go to 0. Right? Okay, so from the definition of the Wasserstein distance, you can extract the solution for the optimal copula between rho k minus 1 and rho k, and evaluate its push forward along psi. So p tau is the push forward of p in this case, so it integrates like p composed with the appropriate vector field across all test functions. And this difference is bounded above by the definition of P by the following expression involving phi tau and the difference the integrand in the Wasserstein distance in between rho k minus 1 and rho k. Remember, P had marginals rho k minus 1 and rho k, and satisfies the definition of the Wasserstein distance with optimality. Okay, so you can take, in this previous equation, you can take limits. You don't really know that the limit of this differential quotient exists, but you'll recover that later. But regardless, you get the fact that whatever this limit is, it's smaller than the right-hand side here, which is y minus x, evaluated times the vector field psi evaluated at y. This is just something that you get by taking the limit tau in psi here. Okay, so all of this implies that so together with the evaluation for E and S put together, and equation 32, where we started off with the variational quotient, plugging all of these in implies that this differential quotient is greater or equal to 0. And kind of weirdly enough, you get saved by the fact that this is symmetric in psi, so you can move psi to minus psi, and it means that this is actually held with equality for all test functions. Okay. Sorry, not for all test functions, for all vector fields. The test function has been chosen previously. So you're very close to what you'd like. Here in the left-hand side, you would actually want to have the differential quotient for rho, so that you can recover the partial derivative with respect to time of the rho vector field. But of course, we haven't gone to that point yet. So again, in order to get our hands on the difference between rho k and rho k minus 1, we again use the Wasserstein distance, which is given by P. The definition of P means that all test functions zeta integrate this way with respect to x and y, which is to say that you can in turn approximate this quantity, which is the difference between rho k and rho k minus 1 and the previous thing that we had in this left-hand side. So you can approximate the difference between these two by the supremum of the Laplacian of zeta and the Wasserstein distance between rho k and rho k minus 1. Okay, so in particular, by making the choice that psi is the gradient of zeta, this allows you to express the differential quotient between rho k and rho k minus 1, plus the right-hand side of the Fokker-Plank equation, the integral right-hand side. So this is effectively after taking the dual differential operator by integrating by parts, and it's bounded above by this constant times the square of the Wasserstein distance between rho k and rho k minus 1. So what you'd like to do at this point is take the limit and sum this equation. But first of all, in order to take the limit, you need to know that the limit exists in some sort of way. This may not be completely obvious, but it's actually fairly easy as a consequence of standard convergence arguments for functions in L1. So fairly typical results allow you to say that these limits exist up to subsequences so long as the sequence is uniformly bounded and is equi-integrable. Equi-integrable or uniformly integrable means that the contributions from the tails of these distributions in L1 they're kind of uniformly bounded. Obviously, the tails in L1 are very thin because these are L1 random variables. But the additional property that the supremum over the integrals over the tails is bounded. This is called equi-integrability. And this effectively allows you to say that you can at least pass to weak limits of the sequence rho h up to, let's say, taking a subsequence. So this is one ingredient that you need. The second ingredient that you need is effectively this lemma, which summarizes what I promised here, which is that as you take h to 0, the Wasserstein distances between these individual iterates also goes to 0, and furthermore, it goes to 0 in this kind of controlled way. So there's this linear behavior in terms of h. So you also need to have the particular description of the function gamma that I wrote there. All right, okay, but nevertheless, summing equation 49, which is this, and passing to the limit. But passing to the limit as k tends to infinity allows you to recover the integral version of the Fokker-Plank equation, which means that anything that satisfies this is a weak solution to the differential version, which is exactly what we wanted. So, okay, this is skipping a bunch of elements of the proof, which doesn't really show convergence in L1 of R to the n for every t. It shows this slightly weaker statement, but you can, again, with fairly standard PD arguments, pass from 0t to just small t. And it doesn't show smoothness of the solutions. Again, you need to show smoothness. Various bounds on the moments and the energy functions haven't been argued for. And also strong convergence of the original solution hasn't been argued for. But okay, so the idea being that just starting from the minimizing movement scheme, you can recover the solution to the Fokker-Plank equation. This is a fairly ubiquitous argument in all of mean field theory in recent machine learning papers. So effectively, over the next couple of sessions, whenever we invoke these types of arguments, we won't go through an individual proof like this. And even though arguments there differ, especially when the coefficients actually depend on the distribution itself, it's just much easier to kind of come back and say, okay, there is a modification of this argument in place. And hopefully at that point we can live with the intuition that you can then still recover these solutions. All right, so this is more or less it for today. Next time we'll go to look at the convergence statement, so not the stationary solution statement, but the convergence statement for noisy SGD. And we'll also speak a little bit about what happens for regular SGD and why you don't actually get global convergence at that point. Okay, so that's about it. We barely managed to fit even with the delays, so we can do questions.
So here, this is supposed to be 1 hour or 1.5?
I think 1 hour now.
Okay, perfect. So this, so I've seen this paper that you presented This proof cited many times. It seems to be a very important paper. I thought it's a very important paper in optimal transport because people don't know. I mean, without this, I guess people wouldn't know how to actually simulate optimal transport in practice, how to change I guess the x variable in a way that I mean, if you have a set of I mean, in this case would be weights, right? But let's say we don't have the problem of optimizing a neural network. Let's say we have the problem of finding optimal transport from one distribution to another. Then using these theorems, what we can do, we can say, okay, our optimal transport is defined by geodesic Wasserstein law. I'm not sure if I'm using the correct words. But then, because this is equivalent to a Fokker-Plank, and the Fokker-Plank is equivalent to I don't know how to call it. I mean, physicists call it Langevin equation. So it's basically
the diffusion equation.
Yeah, the diffusion. Then I can just run the diffusion, and I know that I'm actually doing the optimal transport.
Yeah, exactly.
So this is optimal transport people. I think they use this in that way. Right? I mean, they make use of this result in that sense, I think. So what I'm still missing, I guess this is maybe coming in the next lectures, is why is this relevant for neural networks? So is it because I think you mentioned something like proving global convergence? So why is this useful in that context?
Well, I don't know if it's so these are kind of two orthogonal pieces of the puzzle. It's just that the argument, these types of arguments kind of pervade most of the literature, so it's easier to kind of understand it in the slightly simplified setting. Again, for the distributional dynamics equation of the neural network, which we haven't shown. So we haven't shown that we converge to this type of behavior yet. This is something that we're going to see next time. But if once you converge to this type of behavior, you still want to study the stationary solutions. And again, here the behavior is more complicated because the potential psi doesn't just depend on theta, also depends on rho.
So in which circumstances it does not depend on one, for example, you have linear activations, or there are like clear cases where because if it does not depend on rho, then it reduces to the Boltzmann-Gibbs case, right?
Yes.
So
I guess.
Is there like specific case, for example, a two-layer linear neural network or something like that makes it become so simple then that it does not depend on rho?
So you can see what psi is here. It's this V potential, which doesn't depend on rho, and it's the integral of this U kernel. The U is given by this. So if
Sigma star will be just.
I think it will always depend on rho because you're integrating against the. No, I think it will always depend on rho, even for linear activations, because this expectation, I mean, it can be, let's say the product of two linear convolutions here, but I don't see how you get past the fact that you have to integrate with respect to rho. The point is, whatever you put in U here, I don't think you can get past the fact that you need to integrate with respect to rho, unless maybe if theta prime disappears somehow from U, then yeah, that integral is one, and you're just left with the thing that's being applied there. but as long as there is, non-trivial dependence on the weights in both factors, I don't think you can get it.
So I guess what I understand is so the stationary solution of the Fokker-Plank, we know is going to be, well, the stationary solution of that equation is going to be the distribution, the asymptotic distribution of the weights in this neural network.
Mm-hmm.
It seems like we are mostly interested in that, not in how we get there. Because the thing is this. So even before this paper by Michael Jordan, we already knew that the solution of the Fokker-Plank is minimizing that function, right? So in practice, this work, all these theorems, why are they important? They are important because they make not only we can match the solution, minimizing this functional versus running this Fokker-Plank to asymptotically, but we can match the entire dynamics of how we get there.
Yes.
Right.
Yeah.
So it sounds like then for the neural networks, it sounds like then we are interested in this dynamics,
Mm-hmm.
right? So, but then this cannot be just so the question cannot be just whether we have global convergence, because it sounds like we are interested in how we converge, right? So why
you're
do
also interested in bounds, right? You're also interested in asymptotic bounds, I guess, if you care about how fast you converge. So the idea being that the picture is something like this. There's two sources, two limiting processes. So one of them is the n going to infinity, right, which is giving you the mean field approximation, and the other one is t going to infinity, right? Or let's say the k number of SGD steps.
Mm-hmm.
The convergence is slightly complicated. So if you if you look at how this behaves, it's not like so in order to recover, somewhere here is rho t, right? In order to recover rho t, you need to take more and more gradient steps. So the convergence is somehow like this, right? So for each individual thing, there n and t over epsilon are related because n and epsilon are related. So in order to recover this element here, you need to have knowledge of the entire SGD dynamics of the system. So I guess maybe this partially addresses the reason why you can't just jump from this corner here to this stationary point here.
Okay, and once we use this, and we know we can prove convergence. We can make statements about the convergence of these neural networks.
Mm-hmm.
So in practice, maybe this is a question for the next lecture. So, but in practice, what do we do with it? Like,
so in practice, you also have some asymptotic bounds, which tell you, okay, how quickly you converge to this dynamics as n goes to infinity. So you know that, let's say, past a certain point, you uniformly actually, so this is the point, you uniformly approximate this fairly well.
For example, for NTK, convergence is n is pretty bad.
I mean, I don't remember exactly what pretty bad is. It's yeah, it's some, I think, linear or sublinear of like O n or O, and epsilon
sorry,
or something like
I
that.
was thinking for deep when you also increase the number probably. Yeah, never mind. Maybe we can talk about this another time.
I mean, yeah, it's, definitely this is going to be something that we will be looking at. So yeah, so the idea being that yeah, you want to know what the behavior of this thing is, and you kind of also want to know how many stochastic gradient steps you need to take to get something close to this after you have, let's say, at least these many neurons or something like that. But this is not always possible. And as you'll see, especially for more complicated neural networks, especially for deep neural networks, this stationary dynamics of the solution is not well understood at all. So even though for two-layer neural networks, you have results that show global convergence, for higher layers, I don't think you do. Although again, there is like another branch of the theory which handles it with completely novel techniques. So none of this traditional PD dynamical systems analysis. And there, I think you have maybe slightly stronger results. You also have a result for three-layer neural networks that was published a year ago in NeurIPS. And I think the same people who are working on that, who are doing this neuronal embedding framework, are also working at extending for n layers and above. So a lot of stuff is also stuff that I don't know. Part of the reason why I wanted to do this was so I can force myself to kind of get a more global picture of what's going on.
Can I ask a question?
Go.
This normalization that gives us this law of large number kind of results. So how crucial is that normalization? Basically, what if I change the normalization to get like central limit theorem kind of results? Or
so it's absolutely essential for the type of convergence that is given here, as in the proofs don't work otherwise. If you change it to something like scaling with 1 over square root of n, that seems more like what you do for NPK, right?
Yeah, exactly. So once like maybe they're not really comparable because of the difference in this normalization.
I don't even understand what it would mean, because what you're at some point. So okay, so at some point you are using the fact that you are replacing empirical distributions, right? So 1 over n times the sum of delta functions, right? You're replacing the empirical distributions by their let's say by the sample limit, right? If you normalize these by 1 over square root, then you don't get convergence to the distribution you're sampling from. So I don't think it's
it converges to a random variable.
Yeah, no, I think it doesn't converge to something that has a density in this case. So if you just imagine you take samples from a Gaussian, and you sum the delta functions around those samples, but you normalize them. You don't take the average, but you normalize them by 1 over square root of n. You don't, yeah. The mean of that thing tends to infinity. Yeah. So
the mean itself converges to random variable. So the mean is random.
Yes. Yeah.
Would it be interesting to look into like a law of iterated logarithm?
I think somebody asked that question before. I've heard that question before. A law of iterated logarithm for neural networks. Was it you who asked it?
I don't remember.
Yeah. No, I think I heard this quite a while ago. I mean, maybe Satoru also independently asked it. I actually think you asked Alberto, didn't you? I am fairly sure that you asked.
No one is taking responsibility.
No, I don't even understand exactly what you done.
So let's change the normalization.
Yeah. 1 over square root of n log n, right? Something like that. Yeah.
I mean, we discussed before. I gave a seminar about using different normalization when taking this. But yeah, I mean, I'm sure that it matters a lot.
But what do people do in practice? It's usually like a square root n, right?
Well, so it depends, because it depends also on how you scale other things.
But this here,
Initialization was one by square root.
I think the most popular one.
Gives you very nice output at distribution.
So that makes sense.
But that's okay. But that's just the weight initialization,
Yes,
right?
yes.
Yeah, that's just weight initialization. I guess this is more like why individual batch normalization techniques or something like that are supposed to keep the the distribution of the activations more or less Gaussian, so that they to keep them standardized. Sorry, not more or less Gaussian. But again, I don't think that this relates to this. So the reason why you have this 1 over n here is specifically so you can you can replace these empirical distributions by the the original thing that they're being sampled with. We're going to see next time exactly how this works.
At some point, I remember asking this question because I remember the two different normalization of the mean field and NTK. And then I was asking, okay, but what people do in practice? Is it more like one or the other? And then I think I answered myself, but I don't remember. Yeah. So I think it was much more complicated because it depends on many other things. It depends on how you initialize the weights, how you scale the learning rate, how you scale also, basically also how you initialize the weights and also how you scale the learning rate.
Maybe I made a mistake in explaining this actually. So this is, so for a fixed neural network, this is just a fixed constant, right? You can subsume it into the activation function. It makes no difference. Like you can scale the activation function down by something, right? So this is just something that says how does the sequence of neural networks behave when you want to increase the number of neurons in the layer. So for a fixed neural network, this is not. This is not a normalization of anything. You understand what I'm saying?
Of course, it's fixed for a fixed neural network. Yeah. But the question is, when you scale up neural network.
Exactly. Yeah. When you scale up the neural network, yeah, of course. How do you?
But no matter which way we interpret it, if I change the power of that n, if I change like the n in the denominator of the square root n or square root log n, that the whole thing changes.
You don't recover the same result. Obviously.
It depends also on the learning rate, because how much you change the weights when you train, right? So for the NTK, there is an implicit. It specifies both how you initialize the weights and how you scale the learning rate.
Schedule
and basically, in a way that in practice, in the limit, the weights don't change.
And here the same way.
No, but here the weights change, the distribution change.
Yes, true.
So that's the main difference. The main difference is that in the NTK, the distribution of weights basically doesn't change, and the mean field it changes. I mean, it's all about how the distribution changes.
Yeah. So there. By the way, there's a particular kind of schedule given by this psi function which dictates your learning rates sk in terms of epsilon and then so here as well the learning rates are not. I mean, they're fairly fixed. Okay. I can't tell if is anybody trying to ask questions online. Would we have heard?
Yes, I have one question. So,
go ahead. Yes.
In the summary, does the mean field theory can prove that the SGD in terms of what? So in the summary, in your summary, I saw that the mean field theory can prove SGD converges, and it converges in terms of what kind of meaning?
So, so again, there's two things. So mean field theory is this description of convergence to these distributional dynamics equations as the number of neurons tends to infinity, and also for a particular schedule for the SGD step, right? So this is one thing. It's approximating the solution to this equation, and now the solution to this equation still depends on time. And the second thing is, okay, this equation as, let's say, some sort of diffusion equation on weight distributions, this equation itself may also have some stationary distributions that you might be interested in. So you, as you let time to infinity, tend to infinity, maybe you get a particular interesting stationary distribution. And in particular, do you get a stationary distribution where the risk is zero?
Okay.
Right. This is kind of an orthogonal piece of the puzzle. For the traditional Fokker-Plank equation, right? You know very well what the stationary solutions are. So the lecture today was not about what are the solutions of the Fokker-Plank equation. Today we were trying to figure out what's the connection between the Fokker-Plank equation and gradient descent in Wasserstein space. So maybe to kind of add, like, to help clarify your question a little bit, right? This population risk, right, looks like it's some sort of quadratic functional on rho, right? But it's not, or it is, but not in any way that matters, because the gradient descent doesn't happen in L2 space where this functional is convex. Gradient descent actually happens in Wasserstein space where this functional is not necessarily convex anymore. If this functional is convex in Wasserstein space, then you converge to global minimizers as t goes to infinity. Okay, but it can happen that equation 6 is not globally convex. Sorry, globally is not Wasserstein convex. Is not displacement convex, right? And then you don't really know anymore whether you're converging to kind of global stationary states or what exactly is happening, right?
Yes.
So the only thing that we kind of elucidated today is the fact that somehow you are performing some sort of gradient descent in a particularly well-defined metric space on a functional such as this, right? Or actually rather this. The upshot being that for something like equation 12, which corresponds to not to normal SGD, but to noisy SGD, so actually SGD with this added Gaussian perturbation, and also you notice there's a 2 lambda theta k term in here. This comes from an L2 normalization. So with this extra normalization and this extra bit of regularization coming from the noise, then you do recover this slightly more tractable distributional dynamics equation, which is similar to Fokker-Plank. It's actually called at least as far as I know, this is called the McKean-Vlasov process. A McKean-Vlasov would also have coefficients in here that depend on rho, so it's somewhere in between, I guess. But the original paper by May and Montanari, they actually studied the stationary solutions to this equation and show that you can still, recover this good global convergence.
Okay. I see.
So it's for very particular setups of the SGD and also particular shapes of the neural network, you do have this global convergence result, but it's not it's not in general available. Yeah.
Okay. I see. Thanks. So I think that we should almost run out of time.
Sure.
Yeah. So does anyone have any question? Okay, if there's no more question, let's thank Alex for this instructive presentation. And after this meeting, I will upload the recording video to our YouTube channel that everyone can be free to watch. Yeah. Thank you, everyone. And see you next time.
Thank you. Thank you. Bye-bye.
Bye-bye.
Thank you.